looking for the large volume axiverse.
Okay, thanks very. Is this working? Or not? No. Sorry? Yeah, it's light up. Maybe it's just not close enough. Can you hear me at the back or not? Is that? No. But that's inevitable, unfortunately. Okay, hope. Is that working now? Yeah. Technical difficulties, yeah. I mean, the thing's on. Hello? Oh, that's better. All right, so I just have to shout. Okay. Okay. All right. Thanks very much indeed. I'm going to be continuing on from, to a certain extent, from what Michele was saying, and then also leading into Javier's talk afterwards. So, trying to form some kind of bridge here. So, Michele was discussing the moduli stabilization and efforts and the state of the art in actually building models in the large volume scenario. And now what I'd like to do is to have a look at some aspect of it now in terms of how we can perhaps detect it and learn something about the global structure. Now the motivation, that is something that's motivated me for a few years now, is that in string theory you have lots of different fields, so you never just get the standard model coming out of it. You always have your additional fields such as moduli, which we talk an awful lot about, but also typically you can have many axion-like particles, and indeed they've already been mentioned several times today. In addition, you could have RRU1s in type 2 string theory, or you could have open string moduli and exotic matter. Those latter two are restricted to be somewhat heavy, but you could have hidden matter or hidden gauge groups, for example, hidden U1s, and that's something that I've certainly looked at in the past, but today I'm going to be talking about the axions. So the beauty of these things, so the axions and the light U1s, is that they're actually very light, and you can detect them in all sorts of different experiments and learn something about the global structure of your theory. I mean, for example, you might be able to answer the question, what is the string scale in this context? So this is kind of some top-down motivation for studying these things. And generically, we lump axions and hidden U1s and things like this together under the name WISPs. So weakly interacting, and by which I mean extremely weakly, hence the capitals. Slim being much less than an electron volt, for example, particles. And Javier is going to be expanding on these at length. So I don't think I'll get to talk about hidden U1s, but maybe you can ask me that, and we'll see. Okay. So the bottom-up motivation for these, on the other hand, is that there's actually a huge number of experiments searching for these. There's really an awful lot of interest in the experimental community, and so, for example, there are haloscopes, helioscopes, beam dump experiments, light shining through the walls experiments, and even the possibility now of molecular interferometry. And of course, there's the Planck satellite, which may detect isocurvature and tensor modes and all sorts of these things. So there's the combination of the cosmological observations and also the really quite cheap laboratory experiments being done, which can probe really very weak couplings via sort of high intensity effects, which is equivalent to probing extremely high energy scales. So I would ordinarily give you some nice pictures of these, but I've seen Javier's talk and they're all in there. So you'll have to wait and to trust me on that. Also, there are some other good motivations. For one, the axion is a strong, is the leading candidate for the solution to the strong CP problem. So we all kind of agree that we probably need to have an axion in our theory. This is somehow perplexing because a lot of model builders seem to ignore them or leave them out. Also, they're good candidates for dark matter, as has been mentioned. But then something that I'm going to make something of is that there are actually also these additional hints from several different astrophysical observations that there might be an axion-like particle that's actually very light but couples somewhat strongly to the photon. So if this is so here's the normal coupling to QCD. This is the coupling to photons, and this is coupling to electrons, and these are kind of the three most important quantities in the theory. So here, this ratio of the decay constant to the coupling to electrons with this value offers a solution to the non-standard energy loss of white dwarfs. But then also we actually see too many very high energy gamma rays propagating throughout the universe, and that can be explained with this ratio. At first sight, these don't look the same, but then of course you see that if you have this ratio of order 10, this explains both of these. And then there's this third suggestion that of steps in the power spectrum at a critical energy of 100 GeV, hinting at possibly a mass for this guy of the order of 10 to the minus 9, 10 to the minus 11 electron volts. So this is something that we're going to be looking to see if we can actually realize in the large volume scenario, and I bet you can guess the bottom line. So the interesting thing also about these is that there are several future experiments could actually probe these values. So the next generation of ALPS, light shining through the walls with this value here. The next generation of helioscopes, as you cast at CERN, can really sort of extend into this regime. And then of course there are haloscopes, which are searching for axion dark matter. And then this recent possibility, the molecular interferometry, which would even probe possibly gut scale axion dark matter if it's the QCD axion. So this is just a summary of the constraints here as the ratio of the decay constant to the different couplings. So this is for the cosmic constraints on dark matter here via the QCD coupling, and as has been already mentioned, the upper bound on this is very woolly. Then there are the constraints from white dwarfs and horizontal branch stars and cast. And there's some constraints from the supernova 987A, and then this is where the hints lie. And of course, you shouldn't be fooled by the fact that they don't seem to overlap, because of course they're for different coupling constants. These are relevant. Okay, so now I've kind of given you the motivation. This is the overview. I'm going to talk about how the large volume scenario gives you an axiverse, which Michele has already mentioned a little bit. Then I'm going to talk about what the properties of the axions in this axiverse are, what their masses are, what the couplings are, and so on. And discuss briefly conditions for actually getting a QCD axion, and then talk about some explicit models, and finally some cosmology. So the large volume scenario, if it has several Kähler moduli, if you have, for example, of the order of 100 Kähler moduli, then you expect actually the vast majority of these to be very, very light or pseudo-massless. And the reason for this is that, I mean, you only actually need one non-perturbative effect to stabilize the volume in the large volume scenario. And then the rest can be stabilized via D terms, alpha prime and G string effects, and the G string effects can be open and closed string loops. And with the combination of all of these things, you could actually stabilize the whole set of moduli. I mean, it's true that you may in addition add in extra non-perturbative effects, but these are typically non-generic, and also there may be an issue with chirality there in terms of whether or not they'll ever actually be generated, at least for single instantons. So therefore, you know, what you expect is that, as Michele said, once you require there to be a visible sector, you actually get 2 or more light axions left over once you've interpreted once you've included, for example, D terms, vanishing D terms at leading order, so to cancel the 1 over volume squared potential. And then and each non-perturbative term, when you consider that eats an axion, then you get this constraint, and Michele has already mentioned it. So as a result of this, we can then what we'll end up with is actually further contributions to this, which can give further contributions to the superpotential or Kähler potential, which could give masses to the axions, but they're going to be much lighter than the ones generated by the single instantons. So, what are the properties of the axions in this axiverse? So we can these come from Kähler moduli, so we can just dimensionally reduce the 2B action and look at the couplings. These are the couplings via fluxes on branes. I'm only considering the even forms. The odd ones actually somewhat less interesting phenomenologically, and also there are the issues to do with stabilizing those moduli. So I'm just going to ignore those. But to be honest, you can sort of carry through the analysis of these more or less the same. So you can write, the kinetic terms are given by this term, and here it's showing which axions are eaten up. And this is the kinetic terms for the axions. There you have a mass term for the U1s, and then these are the couplings, and you can just read off what the axionic couplings are. So one thing that I wanted to point out is that the axions are periodic fields, and in this basis they have a periodicity of m Planck. What we define the decay constant as is actually the periodicity of the field. So you can find out what the periodicity of the field is just by diagonalizing this matrix. So this is just the decay constant is then just given by the eigenvalues of this guy. And then you can write down some matrix to diagonalize these and read off the couplings to the gauge group. So you get this expression here, which is slightly cut off. So I mean that's all fairly straightforward. So this gives you this first ratio here, which is what we're going to need for phenomenology a bit later. Then, okay, I'll discuss a little bit about what what sort of sizes of decay constants you can get. So you can actually make an argument about locality, that the axions that propagate throughout the bulk will couple with inverse Planck strength, whereas axions which are local and confined to some space, for example, the analogues of blow-up modes or twisted states, these will couple with inverse string strength. Now, given that the couplings depend on this ratio here of the decay constant to this thing which depends on the kinetic terms, you can also make the argument that because you're integrating the coupling over the size of the brane, the decay constant has to be inversely proportional to the volume of the forebrane in the case of a non-local axion, which you actually just find that this coupling is just of the order of the string scale for a local one. And this is borne out, for example, if you try to calculate what the decay constants for Swiss cheese calabias and then we'll also look at K3 vibrations, and you always get this generic property of this is always borne out in the examples that we try. So, for example, here for this Swiss cheese with this volume form, you can work out what this kinetic matrix is, and here are the eigenvalues, which exactly conform to this when you note that the size of the large cycle is of the order of the volume to 2/3. And then you can plug this in to the Lagrangian and write down what the axionic couplings are. So here indeed we have the large cycles inverse Planck strength coupled, and then the small one couples with inverse string strength. So what we note is that if we want ALPS to be in the classic axion window, then we're going to need to have, they're going to need to be local, and we're going to need to have something like an intermediate string scale. And moreover, if we want to have an axion and an axion-like particle, then we're going to need several intersecting cycles, because they all have to couple to the standard model if it's built on local cycles. So a second example is K3 vibrations. You can play the same game. So you write down this structure, and the reason I sort of labour this is because we're going to look at some more explicit examples which happen to be K3 vibrations. So this is the structure of the volume form that you can write down, and the idea is that you can take these things to be very anisotropic, and then you can get all sorts of interesting properties out of these guys, and moreover that you can actually stabilize these things in quite an anisotropic regime. So when you go to the anisotropic regime, you can have this 2 cycle, which is more or less the same, parametrically the same size of the volume, and then the fiber cycle is just of order 1 or a few. So then you can write down all the couplings, and this is what you get. Now the interesting thing is that the fiber mode and the base both count as non-local axions, even though the fiber itself remains small. And this is because the axion that is associated with the overall volume. It feels the total volume of the Calabi-Yau. Okay, so then we can just write down the axion decay constants here. And what you can actually show is if you generalize this structure somewhat, to a general anisotropic K3 vibration, you can actually show just from the structure of the kinetic matrix that there's only ever exactly one axion with the Planck constant of with the decay constant of the order of the gut scale, i.e. the Planck scale divided by the fiber size, and all the others have a decay constant of the order of m string or smaller even. And this is quite nice when we're going to think about cosmology. So the next thing that I can discuss is about matter couplings, and this is something that's not usually considered. But as I mentioned, normally you worry about the decay constant, the coupling to QCD, and that's about it. Maybe the coupling to photons. But here, what you can actually do in these models is derive what the matter couplings are. And as you mentioned, these are highly relevant for explaining these. Well, for the phenomenology, for example, the constraints from white dwarfs, or indeed for these hints. So. Okay, from global SUSY, it's quite easy to see how these will arrive. If you just write down a kinetic term here and then write down a piece involving the moduli, then you'll find that that when you integrate over superspace, you get this coupling between the fermions and the axion that lives inside this guy. And this piece here, in global SUSY, would just come from the derivative of the Kähler metric. In Surgery, you actually find that there is an additional piece, so an extra bit, which just comes from the overall Kähler potential. And so when you canonically normalize the fields, this is the strength of coupling that you get. So then you can compute this, because there are actually very good conjectures about what the form of the overall, well, obviously we know what the overall Kähler potential should be, and then there are good conjectures about what the Kähler metric for matter field should be. And you can divide that into three classes. So you can have matter that's living on some curve, and it has this expression, matter on some just living entirely on some cycle, and then a matter at a singularity, so in the quiver regime. Now, what's interesting about this is that there is this universal kind of piece here, which is these are two cycle volumes divided by the overall volume. And typically, even for gut scale strings, this quantity is going to typically be extremely small. So, and the only way to get a sort of a substantial coupling to matter fields is for the matter to live on a curve and be in the geometric regime. If you live at the quiver locus, then this coupling is always going to be extremely small. Now, one thing that's quite interesting is that you can actually generate a loop. You can actually generate these couplings to matter fields at one loop. So, and this should, as I've just mentioned, it should be important at the quiver locus. So you can do this in field theory, and to determine what the result is. Okay, so in non-supersymmetric theories, the result has been long known. So you can divide these into axial and vector couplings here, depending on whether or not they've got the gamma 5. And what's interesting is that these guys violate parity, but they're not actually dangerous. There's very few constraints on these. You don't really notice these, but these ones here, you can are the ones which have constraints and you can detect. So the overall expression here, this is just the tree level piece, and then you get a correction from loops at high energy, and then you get a correction from QCD in the case of the case of the QCD axiom. So you can write down what this expression here is. So this is for the QCD piece, which is as long been known, and then in the case of the SUSY theory, you get two different types of loops coming from these guys. And so basically what happens is that the axion coupling to photons generates a coupling to electrons like this. So you can write down what this expression is, and we can take this is a rough expression. Obviously the full expression, I mean, the interesting thing is that it depends logarithmically on the high energy scale. And this could also be interpreted as running down from some high scale. But this is something you can just calculate until you can take the logs to be something of order 1, or well, actually more likely of order 10, and then you have the values for the couplings. The bottom line is that these loop couplings give this ratio of the couplings to photons as being of the order of 10 to the 4, 10 to the 5. Because as you imagine, these things are of order alpha squared divided by 4 pi squared, so these things are really quite small. Whereas in the geometric regime, you get this ratio of the photon coupling to the electron coupling given in terms of the local cycle volumes. And this is of order 10 to 100, which actually turns out to be exactly what we want if we want to explain these astrophysical anomalies. So we're going to take this as a nice sign. Next thing that I should discuss is the spectrum of masses in the large volume axiverse. So as Joe wrote down in a paper, well, about 6 years ago, there are different types of contributions. You can have the superpotential contributions and Kähler potential contributions, which are basically coming from instantons. And they have this form. So what you can then translate this into is an expression for the masses of local axions. So basically it translates into, you have an exponential term with a local modulus in, an n for the number of instantons that's generating it, multiplied by the Planck's. Is that right? I might have put the string scale, and then the Kähler potential, the m3 halves for the Kähler potential terms. So so this is the so the point is that you basically have this exponential logarithm distribution of masses of your axions. You don't actually know what these cycles are, the sizes are in general, but you know that this exponential will be pretty small. So you can actually, if you take this size to be the standard model size, you get a mass of order of 10 to the minus 11 electron volts, but of course this could be, the cycles could be much bigger, and also the more instantons you need to generate the contribution, the smaller this mass is going to be. Indeed. So for the non-local axions, you really, okay, I should have. I should check my signs. At least it's not a factor of 2. Yeah, I don't think that's the expression in the paper, but you never know. Okay.
It is correct.
Yes. Yeah. Okay. Okay. So. I should put these in deliberately. Okay, so there's another point that I wanted to make briefly, which is that, as McKelly pointed out, you have I'm trampling on chalk now. You always have at least one axion in your model, and once you insist on there being a visible sector, then there's also a second one. So you might imagine that. This means that you've always got a QCD axion candidate. So the point is that the axion that's associated with the large modulus is always very light, as we just saw on the previous slide. So so what you could imagine is that you eat up the axion on the visible sector via d terms, and then your volume axion could play the role, it could step in. But actually, it's not true. What happens is when you diagonalize. Okay, so when you diagonalize the axions and integrate out the field which acquires a U1 mass, you find that you get this coupling here to QCD. So this is just the local axion which is eaten, and then this one here is the large cycle one. And okay, that looks fine. It looks like you've got a decay constant of the order of the Planck scale. But then you realize that the decay constant of this guy is actually of order the m Planck divided by the volume is 2/3. So what you actually have here is effectively a QCD anomaly that's inversely proportional to the volume to the power 2/3. And this tells you actually that this guy can't do the job of the QCD axion, as it can't sort of generate enough. Okay, cool. So so basically this is telling us that if we want the QCD axion to be a closed string axion, then it has to be local. Okay, so I'll just talk about some of the constraints on these guys. So so the point is that only the local axions have sizable couplings, and then so we'll have this axiverse of axions with typically extremely small masses. In the large volume scenario, they're going to be much smaller masses than, say, in the M theory axiverse. And then so these guys are. So can you put constraints? And indeed, the M theory people have done some hard work, and they've found that there is this constraint for a window between 10 to the minus 21 and 10 to the minus 11 electron volts, just without requiring any assumptions about dark matter. But then the rest are constraints from cosmology, so from isocurvature modes and dark matter overproduction. So these are things that we have to take into account when we're discussing the cosmology. Now, we haven't done a comprehensive study of the cosmology in this scenario. However, I'm just going to give a few slides just on some thoughts of this. So the point is that the original large volume scenario, when the cosmology was discussed, there was the assumption that the standard model was on the same cycle as the non-perturbative effect. And actually, when you relax this assumption and you stabilize the visible sector by loops, this actually changes the spectrum of the moduli masses and couplings, and this can affect the cosmology as well. So, obviously we've discussed the classical cosmological moduli problem, which says that you need, to have masses of the moduli of greater than the order of 10 TeV. And then these can dominate the energy density universe and inject entropy, do reheating, and generate the non-thermal WIMP miracle, and everything's hunky-dory. But in the large volume scenario, basically you do then have to check whether you get this and whether you're going to have some moduli that can play this role. Indeed, as Troy was saying this morning. So this can be a big problem. So, actually, we can divide the new scenario into three possibilities. One, we can have gut scale strings where the inflationary Hubble scale is smaller than the gravitino mass. Or we can have two different scenarios when the inflationary Hubble scale is greater than the gravitino mass today. So one with gut scale strings, but then we require the standard model on local cycles, or we can have intermediate scale strings and then also the standard model on local cycles. So okay, so first of all, cosmology in the case that in the gut scale case with the high gravitino mass, everything is fine, and you have no cosmological moduli problem because all the moduli are extremely heavy. Modulo Troy's comments this morning, and then you can have a successful model of inflation and reheating. But there are still questions about this. For example, does the sequestering work? I mean, you're talking about a huge gravitino mass. Then you have it can be difficult to build models also with a closed string QCD axion. For example, a Del-Pezzo Sangres, all the local axions are eaten, but they could be a lone local one. Anyway, so these questions remain. We may never be able to detect this. On the other hand, if you can have a gut scale model with a much lower gravitino mass and also therefore much lighter soft masses with somewhat fine-tuned W0. And here you can get around the cosmological moduli problem because the Del-Pezzo modulus here has quite a large mass, and so this guy can decay at about 5 MeV. So this guy can actually play the role of injecting entropy and provide the dilution for you. In the case where you build the standard model on a local cycle, then it's actually the standard model modulus that can do this job. Because it decays at a temperature of about a GeV. And moreover, in this case, we're talking about intermediate scale strings. The non-local axions, they have decay constants of the order of 10 to the 8 GeV. So they're never going to overproduce dark matter no matter what you do. The other thing is that the hidden axions will just be too light to overproduce dark matter. So there we're always fine. So and also this scenario has the advantage that the axions will couple substantially. So we'll have a local axions which can explain these anomalies for us. So this has this attractive feature. Okay, so then just one very brief comment that of axions versus guts, that often in gut constructions, when you use this hypercharge flux to break the U1 out of, to lift the U1 out of the U5, if it's built on a diagonal Del-Pezzo stack, then this will actually eat up the axion that's coupling to it, and then you have to do some extra work to make sure that you actually still have even a QCD axion in your model. But what this underlines is that you need explicit examples for of models with a QCD axion and then potentially with extra Alps. And that's what I'm going to present very briefly now, because I'm going a bit slowly. So what we did at first is that we took two examples from this paper from last year, and the advantage of these guys is that they've stabilized the moduli, they have the right gauge groups, and they have chiral matter. So, and what's more, they actually explicitly have axions contained in them. So they're both based on this K3 fibration. You can write they contain 4 moduli, 4 scalar moduli, sorry. And in general, the volume is not easy to write in terms of the 4-cycle volumes. However, when you choose the fluxes and hence fix the d terms, you can actually simplify the volume. So once you choose the d terms, you can fix 2 of the, for example, in the gut-like model, you've got a stack of 5 branes on one cycle and a stack of 2 branes on another one. You have a Whitney brane and so on. Michaelis talked about this. So then, oh no, you talked about the SU3 times SU2. So I'll talk about that in a minute. So you integrate out the heavy moduli, you integrate out these guys, and this gives you an effective volume. So then, now the advantage of doing this is that you can then work out the axionic couplings, because in this case, these equations are linear. So exactly the same combinations of axions get eaten. And you can just use this guy to work out what all the effective axion couplings are. So you do this and you find that there's a non-perturbative piece here which couples to the axion 7, which becomes more or less C7, which gets eaten by the Gaugino condensate. But you then have a QCD axion which couples with inverse Planck strength. But this is fine. In the second example, this is an SU3 times SU2 model. You do a very similar thing, except you have only one D-term condition. So there you actually end up with a light U1 as well, which is, from my point of view, extremely nice. And then you have this, have a volume form effectively of this form. Again, because you have a linear condition, it's a linear condition on the axions, you can just play the same trick and you can write down the axion couplings again. The interesting thing there is that we have one axion with an extremely low decay constant, but I mean this is because one of the gauge groups is kind of hyper weak. So then this kind of tells you what, this kind of helps you, is encouraging in the search for axion models, explicit axion models. So then what you can do is you can put in, we can now write down a prescription for finding models with intermediate scale axions. And so the general idea is that the standard model has to be on local cycles in the geometric regime. And to stabilize these guys, you can use exactly the same techniques which have been used in the last 2 cases. You can have D terms to stabilize some of the cycles relative to each other, loop effect, and also the which take effect between branes and also between the Whitney brane if it's present, and also the orientifold plane. And the upshot is that for volume forms of this type, you can have a potential at the order of inverse volume cubed of this form. And crucially, you have 2 pieces, and they stabilize this moduli tau 4. And they're clearly, to have an ALP as well as the QC axion, need at least 3 local intersecting moduli. So you can have one D-term condition; it's always there. For chirality, you need that guy, and then so you need 3 local moduli. So what you can do, actually, what we did is kind of wrote down the simplest example which you can study entirely locally without worrying too much about the global embedding, and this is the Z7 blowup. So you can write down the volume form. Okay, so this is the part which corresponds exactly to the Z7 singularity, and then you just don't care about the rest. And I can choose some set of fluxes and branes on this, which stabilizes the 3 moduli, one of them in terms of the other 2. Now this term is no longer linear, so I have to go to the full metric for the axions. This is the form that you get, but you can simplify it by assuming that I stabilize them all at equal values, and I get this form. And then I can write down what the axionic couplings are. And I can see that I get a QCD axion and I get an axion-like particle, and they both couple strongly to their respective gauge groups. And this one here I would interpret, say, as the SU2 or as the photon. So at the end of the day, then how can I explain the astrophysical anomalies? Well, I recall these are the values that I'm looking for, and for this class of models I get this value for the ratio just in terms of the size of this local cycle, and then this size of this ratio in terms of the local cycle volume. This is just coming from diagonalizing the terms, and you can find it with certain choices of the parameters which are really quite natural, just the 10 TeV gravitino mass and so on. We get exactly the values that you want, and these just come out quite nicely. So the conclusions. In the large volume scenario, we expect an axiverse of potentially many light axions, but most of these guys are coupled very weakly and they're very light. They're more or less harmless. But building models with detectable ALPs, or even just a QCD axion, it can be difficult. So it's certainly worth building more and better explicit examples, and certainly looking for axions in any models which you have, because this is really something which we believe is a crucial part of low energy phenomenology, just the QCD axion. And then the final thing is that if the astrophysical hints are correct, we need intermediate scale strings and stabilized in the geometric regime. So, okay, thanks very much.
So you consider the situation with multiple number of actions.
Sorry?
Multiple number of actions.
Yeah.
And some of the actions are eaten by the yuan gauge body.
Yes.
And in that case, this although local yuan symmetries are broken, but still global parts survive.
Yeah.
So that that does not really limit actions. Now the new actions comes in, right? The phase of the yuan charge method. So in some of the action physics, it's very sensitive. Highly depends on the whether you include these additional actions or not. So in your analysis, have you included those kind of the actions coming from the page of yuan charge?
Well, we don't have any VEVs explicitly breaking these symmetries. So I mean,
if you don't break it, then normally you can cause serious problem.
No, of course, but I mean, you can okay, so you've got the black hole information problem. And
not just that. For instance,
yeah.
I mean, in particular, if your U1 is anomalous yuan symmetry of the feasible sectors,
yeah.
then that means that the surviving global yuan group has the Q-sheet anomaly. That means that you have a massive spot, unless it's broken. So you have to break it to make phenomenology binary. Then if you break it, then you have to break it at scale higher than 9 GeV. And then you have to take into account the actions in your analysis. In many cases, I think the result can be very different from the case that you don't include this kind of interaction.
I'll have to discuss that in private, but I think that I think that we would break these things by non-perturbative effects, for example.
Of course, if you break the non-perturbative, then that's different stories. But
exactly.
all of your discussions, we are talking about actions.
Yeah.
We are talking actions whose non-perturbative is negligible, right?
Yeah.
If it's a broken,
or at least extremely small. I mean, it's extremely small. So
yes,
we have a very very light pseudodynamic that goes on.
That's right. I'm worrying about the situations. If suppose that the original action, the action eaten by these bosons, the corresponding non-perturbative is negligible, then you have to include these additional actions from the phase of yuan charge matter field into your analysis, because the physical conclusion can become very different if you include it.
I think that in this case. I don't have something good to say. That I'll have to talk to you in private about that, because I think that I would say that yes, this global symmetry is broken, but it's going to be broken at a very low scale. Actually, I mean, I think that it's just you're going to have a very small mass for this. In fact, yeah, I mean, you know that this will be broken, but this is just going to be like, say, the QCD axion, and then you've got this out, and again, that's going to be broken, but it's going to have a very small mass.
The point is that
okay, so you're worried about sort of symmetries in the Yukawa couplings and things like this that are left over, or the exhibition. Well, okay, yeah, we'll discuss this more in private. Yeah.
You break them with Higgs effect. They are broken by Higgs.
Well, if you do that, then exactly as he says, then you'll get an extra open string axion which will mix and change the properties potentially. So, is there anything?
So let's end up again.
All right,